My name is Mikkel Peters, and this is Lab 3, Black Hole. The purpose of this lab was to find the mass of a black hole by analyzing the motion of an orbiting star, and then to find the initial velocity that a spaceship would need to escape the orbit of the black hole without crashing into a planet. This lab demonstrates the momentum principle, otherwise known as Newton's second law, and Newton's law of universal gravitation. We found the mass of the black hole to be 1.67973 e34 kilograms, and the velocity of the spaceship to be negative 5 e7, 3 e6, 0 meters per second. First, we have to take a look at the momentum principle, which states that net force is equal to change in momentum over change in time. But as change in time gets smaller, this can be approximated as the derivative of momentum. By splitting momentum into its vector components, we could take the derivative using the product rule, which gives us a formula for the parallel and perpendicular components of net force acting on a system. This is the underlying physics concept for centripetal motion, such as seen in an orbit. In this case, the force acting on our star is the gravitational force from the black hole, which can be found using Newton's universal law of gravitation. This force is calculated using the gravitational constant, 6.7 e negative 11, the distance between the system and the source of the force, and the masses of both objects. Since this formula includes both the mass of the star and the black hole, we can rearrange the formula to use net force in order to solve for the mass of the black hole. In part 1, we use a glow script code to approximate the mass of the black hole. This slide shows our initial conditions, including our constants, such as the gravitational constant and mass of the star, as well as a calculation for the star's velocity over time, which can be seen right here. In order to find the net force, we first need to know the velocity and momentum of the star over time. So we start with the final and initial velocities here in these lines, which we then use to find the initial and final momentum by multiplying by the star's mass. We then can find the change in P and V using these lines, simply subtracting the initial value from the final value. We can then approximate the net force by using dp dt, which is the derivative of momentum, and then using the formula from earlier in the theory section, we can find the parallel component of the net force. And then by subtracting the parallel component from the net force, we can find the perpendicular force. We can then print Fnet right here, as well as each component. For the results of part 1, we use this line to find the mass of the black hole, which is just a rearranged version of the universal law of gravitation. And since the orbit is not a perfect circle, the mass is different at each time step, since the force is different at each time step. Therefore, we need to report the mass of the black hole as an average. When we did that, we found the mass of the black hole to be 1.67973 e34 kilograms. For part 2 of this experiment, we need to find an initial velocity that will prevent a spaceship from either being sucked into the black hole or crashing into a planet while trying to escape the system. Here are the initial conditions, including the mass of the black hole we found in part 1, known constants, the planet's speed, and the ship's speed, which we used through trial and error. And these are actually the values that I ended up getting. In the calculation loop for part 2, we find the net force on the planet and the net force on the ship. For each different system, we first find the relative position vector between the black hole and either the planet or ship. Next, we find the gravitational force on the system from that black hole, seen here and here. Next, we find the relative position vector from the ship to the planet, or planet to ship, seen here, and then the gravitational force between the ship and planet in both systems. We then add these two gravitational forces together to get the net force on the planet and the net force on the ship. And in order to make our system move, we then iterate the positions using the position update formula, which uses net force and velocity. Through multiple rounds of trial and error, this trajectory was obtained with an initial velocity of negative 5 e7, 3 e6, 0 meters per second. Possible sources of error for part 1 and 2 could be from the fact that this lab relies on multiple approximations, so it's possible that the outcomes are not entirely accurate. This also means that there could be other forces acting on our system which aren't accounted for in our model. And because trial and error was used, the values could have been more precise. How is net force and its components different from the rate of change in momentum and its components? Well, mathematically, Fnet is equal to change in momentum divided by change in time, so they are very similar. However, finding Fnet and its components requires us to know every individual force acting on a system at every time step. Change in momentum only requires us to know the mass and velocity at each interval, which is much easier to calculate. Therefore, it's a much easier approximation for the net force. What if, instead of escaping the black hole, we wanted to fall into orbit? Well, through trial and error, we found these values to let us fall into orbit with a black hole. Here, the magenta represents the ship and the cyan represents the planet. And as you can see, this required a much lower x component of the speed and a higher y component of the speed.